Okay, so today we're going to talk about two different things. So if you're watching YouTube videos, you get two different YouTube videos. I'm looking at my computer talking to it like I'm talking to a YouTube video, which is the strangest thing. Right, so yeah, we're talking transformations today and post-hoc tests, which, as I said, on YouTube, of course, will be two separate files, two separate videos, but on the podcast will be one. And of course, in the room is just one. So, like I said, transformations. This is why I told you about all that stuff earlier on, about what happens with distribution. You add a constant, multiply times a constant, whatever. Whatever happens in those situations, those are called transformations. So, let's see here. Yeah, there we go. So, sometimes, this is not uncommon, actually. We look at our data with EDA, which is the first step always. You run your analysis of variance, you get nothing. So you just get, T is greater than 0.05, and you're like, that's it. Well, my experiment didn't work. Now remember, this happens with your honors thesis next year. By the way, it almost always does, but for about half the students, this doesn't work. It doesn't matter. No, your marks aren't determined by if your project works or not. Keep that in mind. But anyway, you do all this stuff and you get nothing. You look and you go, nothing happened. Now, the problem is, sometimes nothing happened. So you look and nothing happened, and the graphs are all the same. At that point, you just say, okay, nothing happened. But there are times when you look and you see that the graphs, like you do EDA and you look and go, I see a relationship here. I see that this group is higher than this group, or this group is lower than this group. Something happened, but my analysis of variance didn't pick it up, sort of thing, right? So, why would that happen? Well, I said the other day that if you got, think of it, if you got an F value of 0.03, it's pretty low. That should trouble you. You should think, well, it should never be less than 1. How's that happen? Well, you probably violated an assumption other than the null hypothesis assumption. And if you violate an assumption, it makes the tests, as a rule, it makes tests more conservative, not more liberal, which is good because it makes them less likely to say crazy things, to say, oh, there's an effect and there's not one, except you might be missing something that's real. So usually it's about variances. We can fix problems with variances, a lot of them. Or there's some we can't, but often we can. Design problems we can't fix. So if your observations aren't independent, you did it wrong. You have to start over. But if it's a variance problem, homogeneity of variance assumption of violation, that's fixable. Often. Okay. Do you like that transition? That's cool, right? So what can be done? What is to be done, in the words of Vladimir Ilyich Lenin? These are just for me. You can transform your data. So what I'm saying here is do some mathematical operation on all your numbers that make them conform more to what we want. And what we want is, homogeneity of variance. So it's some kind of mathematical operation that'll fix that. And a lot of people will say, instinctively it feels funny. It feels like you're cooking the books. It feels like you're putting your thumb on the scale and all kinds of other metaphors. It sounds like it's something, you're just cheating. It sounds like you're making up data. Now, because it sounds weird, right? Like, what if I said, oh, we've got a batch of numbers, but I don't like how those are distributed. What we'll do instead with those numbers is we'll multiply them all times 9/5 and add 32 to them. Sounds weird. Why would you do that? Because you're converting Celsius to Fahrenheit. That's all that is. You multiply all the numbers times 2.54. You did that in assignment 1. You're converting inches to centimeters. All you're doing is using new units. So it's totally legit to do this. You're using just different units. So people will say that it's wrong, but really it is. It is so fair. As my old prof used to say, Ian, I told you about the Scottish guy who taught me stats in grad school, if you torture the numbers enough, they'll tell you anything, David. Now, to a point, right? But the thing is, you can do this, it's totally reasonable. And like I said, just think about, we do this all the time with currency. right? You think about it, if you go to another country and they have a different currency, you have to convert their money into your money, or vice versa, right? That's just a conversion. It's just a transformation. What's worth more, $1 Canadian or €1 and 20 euro cents? They're worth the same. Well, it's the other way around. They're worth the same. Wish it was there that way. That'd be great. Our dollar was like worth that much for the euro, but it's still money, right? So just changing your units. That's all you're doing. Okay, that's all we're doing. We're changing our measurement units, which is something that we do all the time. Okay, so here's some examples. What I'm going to give you is a bunch of sort of rules of thumb about when you use what transformations. I would say I'd never ask you about this. I guess I suppose I could, but you'll have all your notes in front of you when I test anyway. So here's the first one I'm going to tell you about. It's the log transformation. So how many people here don't know what a logarithm is? It's okay if you don't. I'm not going to make fun of you. Well, I'm going to do a little making fun of you. But I can explain it to you. But if you all know what it means, okay, I'm just going to assume you all know what it means. Fine. So you do a log transformation. You take the logarithm of a number. So you all know what logarithms are? Okay, you don't? Thank you. All it takes is just tell me. Okay, the logarithm is just taking it's the inverse of doing putting something to a power. So if we're doing the log base 10, oh look, calculus. Holy shit. Okay. That was integral calculus there. That was neat. Okay, so if we have a number like, let's do 10, and we got 100, and we've got 1,000. The logarithm, the base 10 log of those numbers is 1, 2, and 3. So it's 10 to the first is 10. 10 squared is 100. 10 cubed is 1,000. Logarithm. Okay. There's a lot of scales like that. Decibels. Sound, So 10 decibels. Like if you go from 60 to 70 decibels, that is twice as loud. Is that right? No, I'm sorry. It's 10 times louder. It's a logarithmic scale. Okay. So if you are at a concert right by the PA, you're going to get about 135 decibels, which should hurt you. You go to 145, you have to wear ear protection because you're working around jet aircraft. And that's only 10 more, because it's 10 times more. Okay, so or earthquakes, right? Earthquakes. So a 7 earthquake is 10 times more powerful than a 6, and both of those are bad. You'll hear people say this. They'll say, oh, I see that they had an earthquake in California of 5.5. Oh, that's no big deal. A couple of years ago, we had it shouldn't be that big a deal. We had one that was 3.5 here in Ontario. Yeah, that's this. It's nothing. Because it's 1,000 times. 3.5 is 1,000 times more calm than 6.5. So we have a lot of scales in nature like this. Now, we don't use the base 10. Instead, what we use is the base E. So, or sometimes called the natural logarithm, ln, ln instead of log. It's just one of those constants like pi. So it's E based on the natural logarithm. It's roughly 2.72. It's a number that shows up a lot in nature. It's like pi. Here's one of those weird numbers that shows up a lot in nature. E is another one of those numbers. So we would usually do what's called a natural log transformation. So we're just going to take the logarithm of our data, right? Don't feel bad, by the way, if you didn't learn this in school, and you're going, when I ask you if you know what a math thing means, it's not your fault that you didn't. Well, maybe it is. But I'm just going to blame your teacher, and not you. So if you want me to explain a mathematical concept, I can do it, but you got to ask me. Because I'm just going to assume you know what I'm talking about. So well done, Arwen, for saying, logarithms?
I knew what it was, it's been so long.
It's been so long. It's been a lot of these things, right? So a lot of times you guys haven't probably dealt with things like logarithms or geometry, generally. Even if you did calculus in first year. First year was a couple years ago, right? So exponential curves like reaction time. Reaction time is a great example because the curve for reaction time tends to do this, right? Goes way up. So if we think about fatigue, like amount of time you're awake on the x-axis and your reaction time on the y-axis, it's a logarithm. We can also do that with alcohol and reaction time. 1 drink, 2 drink, 3 drink, it's exponential. We all learned a lot about exponential growth a few years back, didn't we, right? During COVID. Now, we didn't all, because some people are still stupid about it, but remember how you'd look and go, oh, there's only 3 cases in some place? I remember here in the Algoma district, up until about July, we had only 13 cases. And it was like, everything was fine. And then suddenly we had 4,000. Because it doubles and doubles and doubles, it's exponential. So in cases like that, you get crazy numbers. Like if you think about reaction time after 5 drinks versus no drinks, you get a lot more variance and a lot bigger numbers. So you're obviously going to have a problem of homogeneity of variance if you're analyzing some data. Now there's a problem here. You can't take the logarithm of a negative number. You can't, okay? It just doesn't exist. You can't take the logarithm of 0. Yeah. So what do? I just add a constant. So like, let's say some of your numbers, the lowest number you have is -5. Just add 6 to all of them, then take the log. Like that's easy. Okay. Chance of any, like some of you might want to work with reaction time at some point with your honors thesis. It's a commonly used variable, and you should log transform the reaction times. So in that case, you're doing log x plus k, not just log x. Okay. All right. So it's going to really suck down the big numbers much more than the small ones. Like, as I said, the log of, the base 10 log of 1,000 is 3. So 1,000 is 3, 100 is 2, 10 is 1, 1 is 0. Wow. Really sucks down the big numbers a lot. Okay. So that's a really useful thing if you've got a variable. Here's another one. So the square root transformation. This is used with counted data. I'm not going to go into mathematically why this works. There's no reason to, and for our purposes, we don't care. If we have counted data, in other words, we're looking at how many times a subject did X, Y, or Z, right? One of the things that, one of my students a few years back, it's almost 20, Jesus, almost 20, was it 20 years ago? 19 years ago, Shauna Barrett did her thesis with me about swearing, and they've told some of you about this in 2606. She was counting how many times people noticed swearing in another room and because of the context. And Shauna, you think I swear a lot? You should meet Dr. Shauna Barrett someday. You know how she signed every email to me after she did her I did a little thing about her professional emails. She signed all her emails to me with, "I fucking hate you." She was in 4th year. It's different when you're my thesis student. Anyway, so that just gives you an idea of how much Shauna swore. So she did her thesis on swearing, and it really should have worked. It actually kind of did. But at first she came to me and she said, "This didn't work. Why didn't it fucking work?" Because that's how she talks. Maybe she doesn't now. She's like a marketing executive with a company of some sort in New Zealand. I don't know. I don't really follow LinkedIn. It bores me. So. But that's where I saw that. And I said, "Well, you were counting how many times they noticed the swearing, right?" She said, "Yeah." I said, "Well, have you transformed it?" And she said, "Why would I do that?" I said, "Did you not pay attention in 3056? And of course, then she told me to go screw myself. At which point, I told her, it's their counted data. You take the square root, it fixes it. So, for some reason with counts, very often you get means that are proportional to variances. Again, mathematically, don't worry why, it happens. So if that happens when your means are proportional to your variances, so if your variance goes up by 2, your mean goes up by 2, that kind of thing? Like double is what I mean by that. They're proportional. So the square root fixes that. So take the square root of the original number. Or if you've got, again, negative numbers, just add a constant, so you're not taking the square root of negative numbers. And suddenly, Shauna's data made some sense, which was kind of cool. Does happen. Yeah, it's an entirely different relationship when you're a thesis student. All right. Reciprocal. You can take the reciprocal of you flip it around over, right? So the reciprocal of a half is 2. The reciprocal of 4/3 is 3/4. That kind of thing. So this is just literally taking the reciprocal. And what this does is it makes the range smaller. So it makes the variance smaller. Because a big number like 1,000 becomes 0.001. And a smaller number like 1 just becomes 0.1. So, 1 just becomes 1. 10 becomes 0.1. So you can see it sucks big numbers down a lot more than smaller ones. This is used a lot with latencies. So times. Running time. In fact, there was a very famous experiment, again, not going to go through the experiment, but by a guy named Abe Amsel, a rat experiment. He was looking at running times of rats on mazes at the University of Toronto, actually. And when he did the work, it didn't look like it worked. And then my stats prof Ian, who was there, said, try taking the reciprocal. And of course it worked perfectly, because reciprocal of time elapsed is what? It's speed. Right? Think about it. Kilometers per hour. Oh, okay. Or really easy. So you do that, and it fixes things. It usually does. And in fact, to the point where with latencies, you might just do that as a matter of course. So you're trying time and speed is all you're doing. All right. So those are ones I think that we all, except for the logarithm, and I think you've all run into logarithms and a little refresher there. Now it gets weird because it's trigonometry. So trig's a little different. We won't have to worry about it. We just know that there are trigonometric functions in our calculators. There are trigonometric functions in SPSS and PSYC. So if you have proportions, so proportions are percentages. So a lot of times we have percent correct in memory research, for example. Memory stuff, we're always using percent correct. Okay. And one of the things that tends to happen with proportions is the two ends, the tails, are small, don't have very much variance, and the middle has lots of variance. Well, think about it. If you're really good, there's not a lot of variance. You can't move around much. If you're at 100%, there's not a lot of movement. If you're at 0, there's not a lot of movement. If the average is 50, well, that could be anything from 100 to 0. It moves around a lot. So the ends are really tight and the middle's fat. We want to make it uniform, right? So the way what this does is it pulls the thing out and makes the tails a little more variable. So here's how it works. It's not even just the arcsine. It's 2 times the arcsine's square root of the number. Look, I don't know why. That one I don't know why that works. I remember in grad school looking at some graphs and going, oh no, I see why that works. I can't remember what the graphs look like. So let's not worry about it. The important point is, though, this is an easy thing to do. You might say, well, I don't know how to do that. No, you don't, but SPSS does. So you just go into transform, and it's a simple process to turn one variable into a new transform variable. So it's 2 times the arcsine's square root. So you take the square root first, then you take the arcsine, then you multiply it times 2. It works, though. When do you transform your data? That's because I get asked that a lot after talking about this. Well, not always. Like, you don't do it as soon as you get data. You don't always transform your data. And in fact, you only do it if the variances are messy. I've done stuff with proportions that I've not transformed because I didn't need to. It's harder for the reader to understand transformed data. Right? Because if I'm telling you that, like, I know what 100% means. It means perfect. I know what 0 means. It means not perfect at all. Perfectly bad. And if we got 2 alternatives, I know 50% means random chance. Right? I don't know what that is in 2 times the arcsine's square root of those numbers. It doesn't help me at all. Right? So if the variances are messy, sure. And these are just guidelines, rough guidelines. They're rules of thumb. They don't always work with every bit of data. But generally they do for these different kinds of data or different kinds of problems with variances. If your data don't violate the assumptions, don't do it. Like I said, I've done a lot of stuff with proportions and counts. And I just analyze counts. I don't analyze counts with analysis of variance. I use a different kind of statistic. So that's another approach you can do. So you might look and go, I'm not going to do any over them. I'll do something else. There's all kinds of something else's. Okay. When you present the data in a paper, in a talk, whatever, you don't present the transform data. Because, again, no one knows what it means. So if I'm showing you a graph of percentage correct, right, if I'm showing you a percent correct graph, I don't know what 2 times the arc sine square root of 100 is. So I don't know how to read that graph. I can read a graph that says percent correct. So you just present the non-transformed data in the paper, and then you, when you analyze it, you analyze the transformed data. You just explain it in your results section. You transform your data. All right. All right. Questions? Yeah. Okay. So that's transformations. That is transformations. We can move on to post hocs.